Hello, welcome to session number 24 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this session I'm going to present to you what is in front of you, a two-stage Cascode LNA, right? And the objective of this LNA is to have a best noise figure you can have, right? So noise figure is basically the ratio of signal to noise ratio at the input to the signal to noise ratio at the output, or rather you can say it is the ratio of the gain offered to the noise to the gain offered to the signal, right? So that would be expressed in dB would be called noise figure, and if it's a pure number it would be called a noise factor. So let's go ahead and design this. Now the question comes is, this is a reference design, right? You can see the matching, right? And this is not by accident that the matching topology looks like this. This has been planned to be like this, right? Now the key here is the interstage cannot be a high pass. It has to be a low pass, because the current which is basically flows through this common gate has to flow through this common source. And then there is a voltage division, so there is a 3.5 volts over here, and this has been designed to be 1.8 over here. So basically this stage was designed with the 1.8 drain voltage, and this stage was designed between 1.8 and 3.5 volts, right? So that was the division, and the currents in both the stages have to be same, right? uh, because that's the only way you can hold this voltage, is to have the same current. So you design this with that in mind. Now let's look at the performance. Okay, so the match here basically is covering, so you can see the in-band performance here. In the in-band performance you can see the gain is varying from somewhere from 19.8 to 19.1, right? And then in between it touches 20.4. So 1.5 dB variation over the entire 1200 megahertz band was my target, right? And return loss better than 10. Noise figure is better than 1.9, right? So this noise figure is along with the losses in the match, and these numbers are going to slightly change. So it is 1.7 on this edge is 1.82. So it's going to be better than 1.9 when you transform this to a layout, right? And then this is the outband performance. These four figures which you see are outband performance. You can see the match is well centered for both S11 and S22. The gain is well centered in our band, and the noise figure is the best you can achieve, right? So let's go ahead and see how did I do this, right? So we'll keep this reference design separate, and I would call this a new folder and say LNA new, right? So LNA new. Okay, so in this case I'm just going to create uh, one design which I will call as save design. I'll call this as uh, LNA 1A, right? So LNA 1 is already there, right? So LNA 1A. Okay, so in this case how I will start is I will start with uh, a transistor of a certain size, and I'll keep the size to be small. So I'm going to choose a certain size of a transistor, and basically the noise figure depends on the current density. So basically the size and the quiescent current basically decide the size, the quiescent current and the size basically decides the current density, right? So I'm going to keep this as 70, and number of fingers is 6. And as you know, we have simulated a via, right? So I'm going to borrow that via. So I'm borrowing that via. Next thing is for stability, right? I might put some inductance in between, right? So I'll start with something like, so in the gain stage we have seen we have put here 40 roughly 40 nanohenry, right? So that's what I'm going to do here. So I'll go to lump components, and I'll pick up something like a 40 nanohenry, or sorry, 40 picohenry over here. Okay, so this will be 40 picohenry. Okay, so now we are set with this. Now we have to be careful that the output side is not going to see a bias decoupling. And the reason it's not going to see a bias decoupling because the current is going to come from the common gate. So in this case, I'm going to use an ideal choke, right? So let's pick up an ideal choke. So go to lump components and pick up an ideal choke. That's this one. Okay, so now I'm going to put the supply voltage here, and the division of the supply voltages from 3.5 I will get down to 1.8 over here. So I will tune this stage for almost half the supply voltage. So I'll go to sources frequency domain and I'll choose here 1.8 volts. Okay, so now we are done with this. Okay, then I'm going to look into the matching part of it, right? So one more thing is there, that there is no coupling cap in this interstage because it has to be a low pass, right? So you cannot have a coupling cap. So for that reason, I would also use a DC block. So there is not much you can do about this, right? So there's a DC block here. Okay, now on the input side, I can put an inductor for decoupling. And if you remember this, I started with 0.5 in case of a gain stage in the previous exercise. So that gives me some insight into what I start with. And I'll start with 1.4 volts, 1.4 ohms as a loss. And then I'll put here a capacitor, which is going to be 2 picofarad. So the capacitor is 2 picofarad. And I'm going to use a via. Okay, so this will be my bias decoupling for the gate side. Okay, now in this case I can do a match, right? So first of all, I'm going to put a bias point, right? So I'm going to take the same stage, the supply, DC supply, and I'm going to put here a DC supply of roughly, let's say 0.5, because you have the idea of some quiescent, right? Okay, later on I'm going to change this also. Okay, so this is our starting point. Sorry. So this is our starting point. Correct? Now I am going to put here a coupling cap or a DC block or a blocking cap, what you call. And this I'm going to keep close to 3 picofarad or 3.5 picofarad. Correct? And we are ready with the initial stage to do S parameter. So I'm going to go to simulation S parameter, and I am going to put in 2 terminals, 1 and 2. So I haven't done any matching yet because I want to design the fly so that you can see what goes into designing it. Okay. Okay, so now we are going to look at the S parameters of this stage and also its stability circles and stuff like that. So let me get the include file here. Okay, and let me put here a simulation controller, right? And this simulation controller, I'm going to just work with in band right now. I'm going to worry about out band later on because I have some idea about stability which I have implemented over here. So I'm not going to worry about that for now. So I will go from 5.95 to 7.15, right? And 10 megahertz is my step size. Correct? So once I am done with this, I'm ready for S parameter simulation, and I also want to see the noise figure, and I also want to see the stability. So I'll put the source stability and the load stability circles. Okay, so I've created all, and then I'm going to hit simulate. Okay, so now it is complaining about the temperatures. So you will have to put an option also here, because all the noise figure has to be measured at 16.85. So I have to set the temperature here, and the temperature I have to set as 16.85, and the nominal temperature also I'm going to set as 16.85, 16.85. Correct? Let me see if I'm recording. I don't want to talk to myself. Okay, so I'm recording. So now if I hit simulate again, okay, it might be complaining about the inductor. Well, it is going to use the model from the database, so that doesn't matter. You can ignore that warning. Okay, so now what I'm going to look at is S11 and S22. S11 and S22. Okay, so they are over here. S11 is over here, S22 is over here. Now what I can do is I can move it up this way, right? And then I can move it this way, right? So to move this up this way, I would need a series inductor on the output side. So I would need a series inductor somewhere here. So it really doesn't matter which side of the inductor you have, because this is the ideal RF choke, right? So it doesn't matter which side you are. So I'm going to put the inductor in here. So I'm going to use a lumped component and an inductor here. And this inductor, I'm going to start with 0.8 nanohenry. And I know it in my practical designs, this would have roughly 1.4 ohm as the loss. 1.4 ohm as the loss. So once this is done, I'm going to hit simulate. And now you see it has moved up this way, and then it has to move that way, right? Now, if I was to move this, then I would have a simultaneous matching, right? So, on the output side, I need what would I need? So I need to move this way. So S22 has to come to the center, and S11 is right there. Okay, so I am going to put a tune on this guy. So let's put a tune on that guy. So you want to see the effect of this, and also I want to say simulate annotate DC. Okay, so hang on a second. So let me just simulate this and look at the simulate annotate DC. Okay, so it is drawing 8 milliamps of current. So I'm going to boost up this to 5.8, let's say, and then simulate annotate DC. So now I'm drawing 20.4 milliamps of current, and if I look at my matching, we are over here. So it has helped. And then I have a tune on this. So let's see if by inductance itself I can tune it out. So now you can also look at the gain. So you can look at S21 in dB. Okay, so the gain is around 12 or 14, right? So I can sacrifice a little bit of gain if this helps in tuning, right? So that's my tune stuff, right? There it is. So now I am going to tune this thing. So now you can see that this is moving closer. The gain is going down. The max value I can increase to 120, for example. Okay, so now this is improving, but then the problem is that this match has moved away, right? So this is simultaneous matching, which I'm looking at. So I want both of them to be at the center for a maximum gain, right? So also I would look at the noise figure, for example, NF2. Okay, so the NF2, rather I'll put it on a different curve so that I can see it properly. So I'll put NF2 here. So if it's order of 2 point something, right? Now let's see, how do I get over here? I can use a series capacitor, and a shunt inductor, right? And on the output side, I am not allowed to use anything other than one more capacitor, right? So first of all, I'll try to move S11 to the center. So I am going to go here and say update, right? So I'm going to update this and close this. Okay, so now I am going to use here a series capacitor is already there, and then I will use a shunt inductor. So I'm going to take this shunt inductor and going to repeat it here. Sorry. And then just rotate it out. So that's the shunt inductor I have, and then I'm going to put here a via. Okay, so now I'm going to hit simulate again and see what has happened. Okay, this has moved this way. Okay, so fine, not a issue. I have this in my tuning hand, and I have this in my tuning hand, and this in my tuning hand, and this in my tuning hand, right? And the idea is to get both of them to the center and get the noise figure as small as you can, right? So get the noise figure as small as you can and get both to the center. That's the whole idea. Okay. Okay. So the noise figure currently is to 1 point something. Okay, so now I'm also going to put this on bias. I am going to boost the current a little and look at the noise figure. So the target here is just to not to just have the match, but also the noise figure numbers. Right? So you understand what I'm trying to do here. Okay. So 1.75, 1.3. Okay. So now the noise figure is 1.7 something, right? And let's see if it can be dropped further. So right now the gain is between 12 and 14, and the noise figure is 1.77 something, right? So this is 0.9. Okay, so let's see what has happened to the noise figure. It's around 1.7 something. Okay, 1.6 something. And so this is, I'm working with the match and the noise figure, correct? So really this doesn't buy much, and the current is too high. So now we are at 5.5 something. Okay, keep an eye on the match also. So now we are at 1.4 something, but then you see S11 is kind of mismatched, right? So we have a series cap and a shunt inductor, right? So we are at a noise figure of 1 point less than 1.5, right? So I don't want to detune this a lot. Okay, because here I also want to look at S11 and I also want to look at S22. And there we are. So we are almost on the edge here, right? On S11, which I don't want, right? So now this inductor, this particular inductor, right? This is L4. L4. So what if I reduce L4 and we are at 1.68, but we are better than 10, right? And what happened to the gain droop? Because the gain droop is also important. This is 13.6 here and it is 12.1 here. So 1.4 dB is the variation, right? So now if I further reduce this, okay, so now I am going to just accept this as is, right? I am just going to accept this as is. It is just centered up, right? So I'm going to say update and close. Oh, we have not looked at the noise figure. So let's cut back our noise figure numbers. So what did we change? L4. We worked with L4. And I'm also looking at the droop, right? So let's see what happened here. 1.6 something. So you have to also worry about the gain droop here. Okay, I'm gonna accept it. Say update and close. So this is my one of the stages, correct? And now what I want to do is I want to construct the other stage. So the other stage is going to come following that. Okay. So I'm going to make another schematic and I'm going to save this as LNA2A. LNA2A. Okay. So in this case, I'm going to use the same size transistor. Of course, you can use a bigger size transistor if you are looking at the power capability, right? So I'm going to say Control C, Control V. Okay, so I want the source to be the input side, because the source would be, it will be common gate, right? So that brings the source on the input side. Okay, so now simulate, clear, annotate DC. Okay, so now this is the transistor, right? Now here I need to put in a voltage, right? And that voltage on the source, which is 1.8. So I'm going to go here to lump components and put a DC feed. And you know that the DC voltage is source is also going to sink the current. So really doesn't matter, right? So first of all, let me also see what is the current here. It's 20.4, isn't it? Yeah, simulate, annotate DC. It's 34 milliamps. So I want to drop this current also. This is too high a current. So this one I am going to drop. How much did I sacrifice on the nice figure? Okay. So really, just 1 second. Okay, let's see. 11 and 13. 11.7 is almost 12. 1.4 dB of variation. Okay, I'm going to accept that and say update and close this and look at the current, because current I want to not exceed 20. Okay, simulate, annotate DC. Okay, it's 18.4 milliamps. That's fine. So 18.4 is the current. So I'm going to keep this voltage as 1.8, right? So keep this voltage as 1.8. So Control C, Control V. So this voltage is 1.8 volts, right? And then I have to have a, so basically, okay, so I need to put a feed here, right? Isn't it? Yeah, because the current is supposed to flow all into this supply, right? So I need to a DC block on the other side. So DC block, lump component, DC block. So I'm going to put the DC block on the other side, right? So now this is the right biasing, and then I have to put a gate. So gate should be a RF short. So if you remember, a common gate, the gate has to be a RF short. So a supply here, something like 2.35 or something, 2.35 let's say, or 2.3, and then this has to be a RF short. So a DC supply will create a RF short, but still I need to put a bypass gap. Okay, because I don't want to depend on the internal resistance of this supply, right? So I am going to keep here something like 2 picofarad, and then I will just put there the substrate via, correct? And there you go. Now this short should be as good as possible, so I'll put there as 3 picofarad. So this short should be as good as possible, and then I need to put here this decoupling. So I'm just going to copy this decoupling in the supply. Come on, Control C, Control V. Okay, so I need to put here the supply. Okay, so this supply is going to be 3.5 volts. There will not be any tune on this. Sorry. So this is our supply voltage, 3.5 volts, correct? And I'm supposed to draw 18.6 milliamps, so I have to adjust this to draw 18.6 milliamp from this. And then I would need a coupling cap. Okay, so I am going to go to lump components and put here a large capacitor. And that large capacitor I am going to keep as 3 picofarad, correct? And then my stage is ready for simulation, right? Okay, so I am going to put all the stuff which I have in the LNA1. So I would need this, and what else do I need? Maybe not this, but this terminal and that terminal. Control C and then Control V. Okay, so all I need is this terminal going to the input. And remember, I can only put here a series inductor and a shunt capacitor because I need to maintain a low pass match here, right? Otherwise I'll not be able to put in currents. Okay, so this I can ignore for now. Okay, so now this is ready for simulation. Okay, so I am just going to do in band first, right? So I'm going to hit simulate and look at S11, S11 and S22, and they are over here, right? Here and here, right? I'm supposed to match it to the center, right? So that it is visible, let me just increase the trace width. Okay, so we are here and this one is over here. Okay, so now this is going to be done by the shunt inductor, isn't it? So if I increase or decrease the inductor, that's going to change that. So let's go ahead. So this is 2, right? So in this case I'm going to work with this inductor, this capacitor, and I need a series shunt capacitor to bring it down, isn't it? And here I can only use an inductor and a shunt capacitor, isn't it? So here I can only use an inductor and a shunt. So what I'm going to do is, okay, so let's do that. So I am going to copy that same inductor over here and rotate it out. Keep it here like that, right? And just hit a tune. Okay, so now that inductor has taken you up, and then the capacitor will take you down, right? So first of all I'm going to reduce that inductance, that is L3. So L3 I am going to reduce so that I come to the 50 ohm stuff, right? And say update schematic, close. Then I am going to use a capacitor here, a shunt capacitor, and then okay, so this is just a matching exercise. Okay, and I'm going to put a tune on this one also. Okay, so a tune on this one and a tune on this one, and tune on this one is already there. So let's see what affects L2. So L2 will bring it this way, correct? And let's say this way. And this inductor L3 is going to move you closer. So there you are. So one is matched. The other one needs a shunt capacitor, right? So I'm going to update the schematic and close it. So I need a shunt capacitor over here. So I'm going to copy this one, put it over here, and now hit a tune again. So the goal is to get them to the center. So the capacitor I added is C5, and C5 is tunable, yes. So that's that. And yeah, okay. So now notice the dilemma. The dilemma here is if you match one of them, the other one will mismatch. That's your dilemma, right? So now what I'm going to do is I am going to do something tricky here. Okay, so get one of the frequencies as close as you can. Okay, so let's say I got this match, right? So I'm going to say update and close. Okay, so this looks like a horrible match, isn't it? Right? Because this spread is so much. So what I'll do is I'll try to implement a broadband match on the output. So what I'll do is I will go here and copy this combination and this guy, right? And I'm going to replace this with a broadband equivalent. So I'll say Control C and I will make a new schematic and say that BBOP, save design. So I'm trying to do a broadband output match, OP. So I'm going to do a Control V. Okay, so now what do we have here? We have the impedance we are going to see. So forget about this Smith chart for a second. Okay, just look at here. Okay, so here I am interested in looking at what the S11 looks like. So I will go and copy the S thing from here. Control C and just bear with me. Control V. Okay, so I'm going to look in band. Okay, and just say simulate. Okay, so now I want to see what S22 at one of the frequency looks like. So I'll go here and put here S11 because S22 is transformed to something. So this is over here. So now what I'm going to do is new marker, and over here in a 50 ohm system I can see what that impedance is. So at the center band it is 4.7 minus J. So it has to be a plus J in case of a. So I'll copy this one right, and then I'll copy this one and I'll put the impedance over here. The impedance is 4.71 plus J because it's a conjugate, right? 24.8, isn't it? 24.89. Okay, so go over here is just that I'm going to keep the ohm as a unit outside. Okay, so it will come in the bracket. That's okay. So now this is what the transistor must have been. Okay, so if I look at it and I look at S11, okay, so if I look at S11, sorry, S33, not 11, S33, this is over here. Okay, so I'm going to put here admittance also. Okay, so the idea is I'll bring it down here and then do a broadband matching. So to bring it down, I would need a capacitor, right? And then I'll hit a tune on this, and this capacitance is C6, so I'll not touch anything else, only C6. So C6 has to be reduced so that I can come down. So let's say I will keep this as 1.2. Okay, so now I am going to use a shunt capacitor to fold this way, come up to here. So update and close. So I need a shunt capacitor. Okay, so that's a shunt capacitor. Okay, so I'm going to copy that over here. Okay, so now this is going to be C7, C6, C7, right? Okay, so it's already coming over here, right? So C6 and C7. Okay, so C6 and C7. C7 can be increased to bring it to the real axis, right? Okay, so that's fine. Say update, close. Then I need the series capacitor to come this way. So I'm trying to do a broadband match. So I'll just copy this over here. Correct? And then this is C8. 6, 7, 8 can be tuned. Okay, so C8 has to be reduced to bring it down further. 6, 7, 8, correct? 6, 7, 8 can be tuned to make as small as possible. That's the whole idea. So this I'll make 3 picofarad. Okay, so this is as small as I can make the loop. So you understood that's what we have to do. Update, close. Then I just need a shunt inductance. Okay, shunt inductance. So I will copy shunt inductance from another one. This inductance will do, right? Control C and Control V. So this shunt inductance I'll keep here in parallel and try to get to the center. So I'll put a tune in this. So we have crossed it, so that inductor has to be increased, right? So this is kind of the smallest loop you can make. So you're not supposed to change C3. Close. No, you're not supposed to change C3. So that would be a mistake, because this is the one which we are trying to transform. Just 1 second. So I'll just take it off from the tune so that by mistake I don't alter this. Fine. So now the idea is, okay, is to work with this to make a smallest loop. That's what we are supposed to make. A smallest loop around 50 ohm. So this can be dropped to 1.0. The smallest loop. So this is not going to do that. This is there, but really this is not what is helping. Okay, so for now I'll accept this and say update and close. So this happens to be our new match. So this one I'm going to copy, and this one I'll put at the output, right? So this one I'll put at the output. Get rid of these. So I don't want this. Control V. And this one has to be flipped around, right? Okay, that should be the way it should be connected. So this is done. Correct? So now we should know that this is C6, 7, 8 and L4. That's the output match. So let's just simulate this or tune this. So now you are looking at this guy. Okay. So now the idea is to wrap this around, the smallest wrap around. The smallest wrap around. That's the idea. Right? So the smallest wrap around we have to create. Okay. So this is the inductor, so we cannot change that. Okay. So this one. Okay. So this one, let's say, is 4. Okay. But then it has to be recentered, isn't it? And then this is my input. Okay, fine. So this is recentered. Okay, and what about my input? So let's see what input is affected by. So the input is L3 and C4. L3 and C4. So this is L3 and this is C4. So C4 has to be reduced, correct? And L3 has to be increased. And C4 has to be reduced. So this is kind of very flaky match, right? But you understood what we are supposed to do. Update close. So I'm going to look at what this looks like. Okay, so I'm going to look at S21. Okay, one more thing we forgot to see. We have to be putting in 18 milliamps of current, not more than that. So simulate, annotate DC. Okay, so we have to simulate, annotate DC. Okay, so let me just simulate this and then annotate DC. Annotate DC. So this is 15 milliamps of current, roughly. So this can be increased a little. Okay, and hit simulate. So we are like this. Okay, this is better than the previous one. So I am going to put these two stages together, but before that, this is 6 to 8, and then S11, S11, and S22. Okay, so we are really bad on S22. We've done better than 10, right? But what I'll do is I'll try to tune this after we put these two stages together, right? So what I'm going to do is I am going to bring in my another stage at the input of this one, right? So this DC feed will go away, right? And this will go away, right? And the stage will sit here, right? So I am going to go, sorry. So I am going to go to stage 1, and in this case I am going to copy this one, right? Edit, copy, and edit, paste. Okay, so up till now everything is kind of with a certain system. Okay, so now this is not going to be there because this voltage is setting that, right? And this is also not there. Okay, so all that remains is this guy. Okay, so now you are looking at a, a two-stage, right? And we should know that L5, L3, and C4 is the interstage. C9 and L7 is the input, and C6, 7, 8, and L4 is the output. And then we can also have a tune on this one, so that's not the issue. So these are also on the tune. So all are on the tune. So in this case, I am going to have the option here. Option is this, and then noise figure is also there, right? So I am going to look at the combine effect. So the combine looks like this. The gain is 20, right? It's just that this droop is too much, right? So what I'm going to do is I'm going to separate these two curves. Okay, so in this case I'll get rid of this one, and in this case I'll get rid of these ones. Right, so the idea is to have the minimum droop and the return loss better than 10, right? Okay, that's the whole idea. And then let's look at the noise figure. So the noise figure 2 is around 1.7, right? And let's also look at the current. Okay, so simulate annotate DC. So the current drawn currently is 18.3. So that both the stages are drawing 18.3, right? Right, and this is 1.8 volts as we designed for. This is 2.6. This sets that 1.8 volts. Okay, so now we are ready with all this. Only the minor adjustment is the gain has to come better than the return loss has to come better than 10, and the gain should not vary a lot, and this noise figure should not degrade. As is good enough, right? So I am going to hit a tune and try 1 or 2 times, right? So we are interested in this. I'm going to hit a tune on this, and this is not required. So now I have to keep an eye on return loss and the matches, right? So now we should know we are not working with we are first working with the interstage. So to see what's the best we can do with the interstage, and then this is the output match. So we are working with C6, right? So C6 is doing that. C6 is doing that, correct? And C6 is doing that, right? So the gain is going down. Okay, so I don't want to lose the gain. So this is L3, right? C6, L3, and then this is the output match, right? So 6, 7, 8. 6, 7, 8 is the output match. So 6, 7, 8 is the output match. So there the noise figure is going up. And that's the match. So what happened to the noise figure? 1.6 something. Right. So it's just that the S22 is troubling me, right? So this is the supply. I'm not going to hit this anything on the supply. Okay. So the gain is going down here. I don't want to sacrifice gain either. So I don't want to sacrifice gain. I don't want to sacrifice noise figure. I don't want to sacrifice anything. But then the world doesn't work like that. You need to sacrifice something, right? Correct? So really it is the output match you have to work with. Output match you have to work with. Gain is 17 point something, right? 17 to 19. So the output match is C6 and 7, and this is stuff, right? So this is 4 picofarad. I don't want to go more than that. And fine, but I have sacrificed gain. I don't want to sacrifice gain. And I have to have a good nice figure. Okay, so what I'm going to do is I'm going to put you on hold. Meanwhile, I tune this out, right? Because this is going to just waste your time, right? So I'm going to put you on a pause. Okay. Okay, so after all this iteration, I have something of this nature, right? I have a return loss which is better than 10 on the output side. On the input side, it is better than 20, right? And then in switch chart, you can see the match like that. And the gain basically is going between 17 point something to, so there is almost a 1.8 dB gain variation. Of course, you can even if you fine tune this a lot over here, really it will not help you. Why it will not help you is because once you start laying out, the matches are going to move, right? So this you should accept as is and move on with the layout, and then adjust this according to the layout, right? Because then you will be seeing realistic queue of the components, and then these variations will not be that sharp, right? So that's what I suggest is once you reach this point of a two-stage LNA, right, where your noise figure is almost like 1.5, 1.6 in this process, right, you can also plot here NF min and see how much scope you are there. So you can still improve this, right? But then you can do a little bit, because the noise figure is not the only thing. The thing is that the gain variation, the return loss, and stuff like that, right? They are also important. And the quiescent is also you have to keep down, right? So right now the quiescent is 18.3 milliamps, right? And this is the two stage which I wanted to design. And just one more second. Simulate, and then say annotate DC. Simulate, annotate DC solution. Okay, so we are over here 1.8 volts. This is 3.5 supply. This is 0.56 or 57, right? So the biasing is like that. So another thing which is important is that how much is the SFDR. So basically we have to look at the compression characteristics of this LNA, right? And in that case you might have to increase the size of this and sacrifice your noise figure slightly. So all these variations are going to be there in a realistic design, right? So the next step for you would be you can do on this what you call a Monte Carlo analysis, right? And then you can do the design centering and all that stuff. Or B, you can start with the layout, right? So I would start with a layout, right? And really not worry at this moment about the yield and stuff numbers, though they are very important. But for learning, this is the starting point, right? So I'm going to stop here, right? I've already spent 1 hour. I'm going to stop here, and what I designed is a two-stage LNA cascode, right? Okay, great. And one more thing I want to point out, people, when they do cascode, if they come from analog background, they just put this transistor with that transistor without anything in between. At low frequencies, it doesn't matter, but at high frequencies, this will not work, right? So that's the only key point I can give here. Okay, so I'm going to stop here, and that's your two-stage LNA with a response which is like this, right? Great. Thanks a lot. Thank you very much.